Hi there. Hope you are deep into reading chapter 2 and doing the homework. This video is going to cover starting at section 2.2 onward. We're going to try and get to through section 2.4 acceleration. We've already talked about quite a bit, quite a few things in this section, and so I'm going to go through it pretty quickly. I'm going to try and explain it. And then there are also going to be some homework problems posted, and I've already started posting those. So there's quite a few examples on there. If you would like to have a specific homework problem, please send me a message and I'll do my best to do that problem. I already did a couple problems that people requested, and I'm happy to do more. Okay, so uniform motion, basically in one dimension. If we draw this motion diagram, then the dots are going to be evenly spaced. Okay, so our particle is moving through space at a pretty even rate. That means if we take a picture every 1 second and we see that it's moving, the distance between those dots is going to be the same. We've also looked at these position versus time plots down here, and we learned that you can get the velocity by finding the slope of the line. Right? And if something has a constant velocity, that slope doesn't change. If the slope of the position versus time graph changes, that means that there was an acceleration. There was a force acting on that particle, whatever it was, and it caused the velocity to change. But as we're going to see, velocity cannot change without a force. Okay, Newton's law. There has to be a force in order for an object's velocity to change or for it to start moving. Okay, Newton's first law. So there must be a force acting on something in order for it to either start moving or for its velocity to change. Okay, so we have a slope here. The slope of the position versus time plot is the velocity. All right, velocity of an object in a uniform motion tells us the amount by which its position changes during each second. And we did this on the last video a lot. So you take the final position minus the initial position, and then you divide it by the final time minus the initial time. And this sign here, right, it's really important that that you do final minus initial, because if you do that, you'll get the correct sign, which will tell you the direction of the velocity. Okay, so uh, the sign tells you the direction of the velocity, so that's really important. So don't forget to do final minus initial, okay, and divide it by, of course, the final time minus the initial time. Okay, now this is going to be our first equation of motion right here. This is really important, so make sure you write this on your card. Ultimately, there are 5 equations of motion, okay, and you're going to need to put these on your card. This is kind of the first one here, okay, and this equation tells us how far an object is moved if it's traveling at a constant velocity. So that means our velocity is not moving. Sorry, I mean our velocity is not changing. This will tell us how far it moved. Okay, but there's no acceleration in this one. So that is really important to keep in mind. Oh man, there we go. So there's no acceleration in this one. Okay, and we get this equation right here, which this just tells us the this one tells us basically how much did our velocity change as a function. Yeah, how much, sorry, how much did the position change if you're traveling at a constant velocity? So I'm going to write that down. I'm going to say equation one. Okay. So you're going to need to make a card, a 3x5 note card for the test. You can put anything you want on it. I don't care. And you're allowed to use that for the test. That's totally fine. Okay. All right. So equation one, delta x equals v times t, right? This is a pretty standard equation. If you're traveling at a constant velocity, this is how far you're going to go. Okay. And this is useful if you're driving in a car, right? Let's say you want to travel 120 miles. Okay. So let's say Evie. Okay, Evie's right here. Evie wants to go to Kansas City, which is let's say 300 miles away. Okay, 300 miles away, and let's say Evie's kind of slow, so V equals Evie. Okay, has a velocity of let's say 50 miles per hour. Okay, and Kansas City. Delta X here is, let's say, 300 miles away. So, how long is it going to take Evie to travel that distance? Okay. So what we're going to do is we're going to put in our numbers. We'll say delta X equals V times T. So, our distance here is 300 miles. I'm going to put miles because I don't want to confuse it with meters. Don't do that. Then this is 50 miles, and we'll put per hour times delta t. Okay. So what do we do here? We divide both sides by 50 miles per hour. So let's say divided by 50 miles per hour. Okay. I'm going to divide both sides by 50 miles per hour. 50 miles per hour. Okay, my miles cancel here. All this cancels. Okay. Then over here I've got 30 divided by 50. That's gonna be 6. Yeah, so 6 hours. So I'm gonna get in my denominator here I have hours. And if you divide by something, the denominator goes to the numerator, right? Um, let's see. Yeah. So you divide by that. So how does that work? Well, basically we could also write this as hours uh over 50 miles. That's the same thing as writing like that. If your denominator has a denominator that goes into the numerator, or you can just invert and multiply. That's probably easier to think about. Okay, my miles cancel here, and then I get hours in the top, and so my time, delta t, is 6 hours. So it's going to take Evie 6 hours to travel to Kansas City, and we've got our first equation of motion up here. Um, we will we're gonna talk about all 5 equations of motion. Okay. And this is our first one. So write that down on your card. This one's gonna be important. Okay. Now, we're gonna talk a little bit about math, but nothing too serious. Okay. In math, sometimes you have a proportionality factor. So physics seems densely populated with equations. Maybe, okay. But I don't like to think of them as equations, and I'll tell you why not. Okay. Instead of equations, okay, I think a better way to think about it, I just for a minute, you gotta open your mind, okay? So instead of all these equations, yes, there maybe are quite a few equations. I like to think of equations as an experiment, okay? Because each one of these equations is actually an experiment, okay? The equations of motion. All right, if you want to go on a road trip, you're going to need to know that distance equals velocity times time because uh that special someone is like, hey, when are you gonna come to visit me? And they want a time of when you're gonna be there, okay? Because if you're the person you're dating, if they ask you, hey, what time are you gonna be there? And you don't show up at that time, you're gonna be in trouble. See, so physics is gonna help you in life. It helps you with your relationships, okay? Because you're gonna be on time, and that's gonna help you in life and with your maybe with your girlfriend or boyfriend, okay? If you're on time, they're going to be happy with you. So, see, not only is physics fun, we just learned that it helps with relationships too. See, you thought physics was pointless. No, no, will just help you in life in so many ways. And I'm going to show you all those ways how physics can help you in your life. But I forgot what I was talking about. So let's just go back to the slides. Yes. Okay, here we go. So all these equations, okay, they have the same form here. It's always y equal or one variable y equals a constant times x squared. Each one of these equations has the same form. Okay, here's kinetic energy equals 1/2 mv squared. Okay, and then over here we have the potential energy of a spring. And it's how much energy we can store in a spring. We'll talk about energy later, but we have this relationship, okay, where we have a one variable is equal to a constant times another variable. Here we have a proportionality relationship, okay? And you can also think of this as basically the slope of a line. This is a linear equation, so y equals c times x. And in this case, c is the slope of that line. So if we want to, yeah, if we wanted to um, find the slope, then we could do that from based off of this line right here. But this uh, y is proportional to x by some factor, meaning we put in a variable for x. So if we put in 2 here, then we get 2 times x equals y. Right? So y equals c times x. We could have y equals c times x squared too. That would be a parabola. Okay. Um, Either one of those is fine. Now, the reason that they're showing you this is because sometimes knowing these relationships can of these proportionality factors will help you to solve certain problems. Okay, for example, if you know that this variable y is proportional to x, okay, then you could find this ratio at different times. Okay, like for example, we can do this with velocity. So maybe c is our velocity. Okay, because we'll often have an equation. Okay, we'll have we're usually going to be dealing with, say, position or velocity. Okay, so we'll have my x position equals my velocity times time. Okay, and so what you can do is, um, if you know what these are, so let's say, all right, Evie is traveling here in some direction, so maybe Evie starts out here, and then sometimes later Evie's there. So Evie's like poof, poof, okay, and so on. So Evie is moving here. Right, so those are, let's say Evie has some velocity. Okay, let's say let's draw some numbers in here. Okay. All right, we said Evie's velocity was 50 miles per hour. Let's stick with that. That's fine. Okay, we can think in miles, and I hope you watched my video about Saturday Night Live, where we talk about units of measure. And Americans, we have a very unique system of measurement. No one else in the world uses that, and quite frankly, it's horrible. Uh, Meters and seconds are way better. But okay. So what do we do here? Well, let's say we know that Evie's velocity is 50 miles per hour. Okay. So let's say then so we'll have, let's say, yeah, okay, so this will be 50 here. Okay. This is going to be 100. and then this one will be 150. Okay. And so EV starts off here. And let's say we know that EV is at y equals 50. Okay. Then well, let's look at our proportionality factor. So we can write that x1 divided by x2 equals um, velocity of EV times T1 divided by velocity of EV times T2. Okay, so we basically just took two equations and we divided one by the other. Okay, so, and I'm going to show you what I'm talking about. So the question might ask you, okay, if we know that at, let's say here at, this is at maybe 1 hour. Yeah, this is 1, 2, 3. Okay. Let's say that at yeah, 100 miles, so we'll say x1 equals 100 miles. Okay, 100 miles. Um and see what, because what happens is my velocities cancel out here. And so now I end up with this equation x1 over x2 equals t1 over t2. Okay? So what you can do with this is you can say, okay, I know that at x1 at say 1 hour, so at t1 this is 1 hour. Okay, I know that Evie was at 100 miles. Okay, so then the question is at yeah, it's 100 miles. Okay, so then at t2, let's say t2 equals 2 hours. Okay, what is going to be my position x2 at that time? Right? And um, since the velocity is constant, it doesn't matter. Okay. And oh, I wrote this down wrong. Let's say, yeah, at 100 miles, okay, that's actually at 2 hours. Okay. So then let's say, what about at 4 hours? Okay, T2 is 4 hours. Well, now I've got this equation down here so I can plug in my time, right? I want to, what I'm after here is x2. That's the thing I want to know. So over here, I'm going to put in all my values. I'll have, this is 100 miles divided by x2. And then I've got my T1 over T2. Okay, so T1 is, that is 2 hours. Okay, and I know that um, T2 is 4 hours. Okay, so what's my time? What distance am I going to be at here? Okay, so see, this is actually kind of useful, and I think there are probably problems in the homework like this too. So it should be very useful. Okay, so now we need to get x2 on the other side. So I'm going to multiply both sides here by x2. Okay, my x2's cancel over here. Okay, they cancel, and then I'm going to multiply both sides by 4 hours, and divide by 2 hours. So this will be over here. I'll have 4 hours divided by 2 hours, or I'll just get a factor of two. Okay, but over here they cancel, so I get x2 on this side. So now x2 is going to equal 100 miles times 4 hours divided by 2 hours. Okay, well my hours here go away. This four is divided by two. 4 divided by 2 equals 2. So this gives me I get 200 miles. That's my distance. This will be 200 miles at x equals 2. All right, so let's look at our plot here. Okay, we don't actually have it on here, but let's continue what we're doing here. Okay, I love to plot things. Okay, and hopefully you will learn how to plot things by hand. If you don't already know that, hopefully you know it, but maybe you don't. But we're gonna plot a lot of things by hand here. So okay, I've got 200 up here, and if I continue my line, where's my prism? Yep, there's my prism. Okay, so I'm going on a line here like this. I got my two dots here. Now keep going, and yep, sure enough, okay, right here, if I draw this up here, okay, that is correct. Okay, so I still have this problem basically two ways. One, I just continued the slope of this line here, okay? Because that means that my particle is at a constant velocity, right? And my velocity is 50 miles per hour, okay? And so it makes sense. I use this formula, these ratios to calculate where I'm going to be at time t equals, okay? And if you're a visual person like me, okay, you can make a plot of this, right? And I didn't need a computer to do this. I did it all by hand. So it's a pretty useful skill to be able to just make a plot like this because you can actually, if you wanted to, you could actually just solve this graphically. You don't even need the equations. Well, yeah, you kind of need them, I always find it helpful to draw a picture like this, and I'm probably going to say that in every video. Okay, well, let's go on. All right, so I think we covered acceleration and we covered velocity. So we covered this proportionality factor. Oh, let's look at this plot here. Okay, here's a position graph of an object. Okay, at t equals 1.5, the object's velocity is what? And remember, this is position versus time. And so if there's a slope, that means that it has a velocity that is not equal to zero. Okay, from 0 to 1 here, the position doesn't change. So that means my particle is stationary, it's not moving. Between time equals 1 and 2, there's a big change in velocity. I can look at this plot here, and it's basically I move 20 meters in 1 second, so my velocity is 20 meters per second. Okay, and it's positive. On the other side here, I can see that my final time is 0 and my initial time is 20. So if I say, all right, and my time took me 2 seconds, okay, it took 2 seconds. Uh, so I subtract my final velocity from my initial velocity, which gives me minus 20. Okay, that's why you do final velocity minus initial velocity, and then you get the right sign because the velocity tells us this thing is moving back towards zero. Okay, it's moving back towards zero. Um, and it's going to have a velocity of negative 10 meters per second. Right? Over here, the slope is positive. It's like this. Okay? That means it's positive. It's positive 20 meters per second. Over here, it's minus 10 meters per second. Okay, so let's look at our plot here. The question says, here's the position of the graph of an object. At t equals 1.5 seconds, the object's velocity is, well, we look here. Okay, on my plot. Here's 1.5. It's in the middle. I know what the slope is here. The slope is 20 meters per second. Okay, so the answer is B. Um, yep, that is the correct answer. Okay. All right, here's another problem. I think we'll just go through this real quick and then we're going to go on to acceleration. Train is moving due west at a constant speed. A passenger notes that it takes 10 minutes to travel 12 kilometers. How long will it take them to travel 60 kilometers? Oh, well, we got this one. Okay. So now that we have that equation, right, it's traveling at a constant velocity. Okay. Um, let's take a look here. We just found that equation. That was a nifty trick. We had x1 over x2 equals t1 over t2, right? There we go. Okay, so x1 over x2 equals t1 over t2. And this is just from our equation, delta x equals v times t. Okay, we could do it for two different times. And so what did the problem say? It said it takes 10 minutes to travel 12 kilometers. Okay, so what? Yeah. Um, so initially, okay, then we're gonna have so I think we can just plug it in here. Okay, so for the first one, um we're gonna say x1 equals 12 kilometers, and T1 equals 10 minutes. Okay? And we know X2, it says, how long is it going to take to travel 60 kilometers? All right, well, now we just plug it in and we solve for T2 and we are done. So let's put those in. We'll say 12 kilometers divided by 60 kilometers equals 10 minutes over T2. Now you're like, Dr. Wisby, don't you convert to seconds? Okay, well, mostly because I don't have to, and I'm freaking lazy. Okay, that's the thing that you need to understand about physicists is we are lazy. Okay, if you don't have to convert, don't. I know I've been doing miles per hour, and in the last video, I was like, don't use miles per hour. It's really bad. Okay, well, you know what? It's okay if everything is just in miles per hour. Okay, so what am I doing here? All right, I'm multiplying both sides by 60 over 12. So I'm going to go 60 kilometers over 12. I kind of do this in my head, okay? Because that side's just going to cancel. And then I multiply this side by 60 over 12, okay? I don't want to skip a step, though, okay? So what's going to happen now? Well, this side will cancel my 60, cancel my 12, and multiply both sides by T2, okay? Multiply this side by T2. So now we've got T2 on this side, and I just got all this stuff over here. Okay, so then I'm going to say 10 times 60 is 600, and then 600 divided by 12 is probably 50. I don't know. I'm gonna get my calculator. Dang it. I should be able to do this. 600 divided by 12. It was 50. I knew it. All right. So, yes, T2 is going to give me 50. 50 what? Oh, we'll check my units here. Kilometers cancel. Okay. So that's going to give me 50 minutes. Boom, we did it. All right, that's my answer. Okay, we used the power of ratios. Okay, wow, that was something. Okay. And the great thing was, okay, we just used this up here. X1 over X2 equals T1 over T2. We don't need to know what the velocity is. If you don't need to know, then don't figure it out. Okay? Just make your life easy. Okay, so we did that one. What do we got here? 50 minutes. Yep, we did it. All right. Awesome. All right, what do we got here? From velocity to position, one more time. Okay. Now we are talking about graphically. Okay, so this is another way that you can solve the problems. Okay. So the displacement delta x is equal to the area under the velocity graph during the time interval t. Okay, so now this is new. Now we're making a velocity versus time graph, right? So if you're on a train, what is your velocity? Okay, let me switch back to my picture. I really liked Bob Ross. He was an amazing guy. It was fun to watch him paint, and so I like to draw pictures and write equations. Okay. Bob Ross is my inspiration. If you haven't seen Bob Ross, you can watch all his episodes. I guess Twitch bought all the episodes of Bob Ross, and you can watch them all. I think Bob Ross is playing constantly on Twitch. I don't know why, but some things in life we don't need to know why. We don't need to understand, okay? You see, the Western mind has this obsession with understanding everything. But in certain Eastern philosophies, they're okay with living with paradoxes. Okay. You don't have to understand everything and have everything make sense. Okay. All right. Let's say you're on a train traveling at a constant velocity, and down here is time. Okay. Well, over time, if your velocity does not change, okay, then it's going to have a constant value. And so every time you measure it, it's going to be the same, right? This is like if you're driving on the freeway and you're on summer vacation, you're probably going to go on summer vacation later. And you're like, oh, I want to go to the Lake of the Ozarks, okay? Or maybe you're going to go to Disney. I don't know. Driving to the Lake of the Ozark, you're chewing on your beef jerky, you're eating corn nuts, and you're just cruising along at a constant velocity. Well, over time, your velocity doesn't change. It does not change. And let us recall that delta x, the distance, is equal to v times delta t. Okay, how much time went by? Okay. Well, let's look at our plot here. Okay. On this side is velocity v. Okay. Over here is t. That's delta t right there. All right. So let's say that we want to know, well, how far did we travel? Let's say this is our first hour, 1 hour here. Okay. And we went for, and you're cruising, let's say 60 miles per hour. I know I'm using miles per hour again. Why am I doing that? Well, the book does it, so I can do it too. Let's say you, after 5 hours on the road, how far did you go? One, two. Okay, so this is 1, 2, 3, 4, 5. So I'm drawing a line here. This is your fifth hour. Okay, you're driving an EV, so you didn't have to stop. Yeah, because you don't need gas. I mean, you have to recharge, but they last a long time, okay? Electric cars, you don't need to put gas in them. You can just charge your battery, okay? And that's okay. Okay, so how do we tell how far we went? Well, the equation says velocity times time. It tells us distance. Yes, yes, it does. And so what we can do now is we can say, oh, well, hey, look, that's a square, man. It's a square. Okay? It's like this side of the square is time, and this side is velocity. Haha. A velocity square. Yeah. Okay. So if we calculate the area under the curve, okay, or just the area of this box, okay, that's going to tell us x. So this area here is the distance we traveled. Yeah. Okay, it's the distance that we traveled. Delta x. Man, this is x. Okay, that is the distance that you traveled. If you compute the area of that box, okay, that's your distance. Okay, now I'll tell you a secret. That's actually calculus. But don't worry, okay, because you probably didn't know that in calculus you just find the area of a box. Yeah, uh they do that a lot, okay? Yeah, you find the area of things. And maybe your function goes like this, okay? Over maybe your velocity changing, okay? But you're like, Dr. Wisby, I am out of beef jerky and I need a soda and I can't think about that. I'm just gonna draw a box, which is actually the same area as this wavy line, okay? That's totally cool, man, because it's the same area. Yeah, it is. Okay. So there, now you know calculus. Find the area under a function curve. Boom. We did it. I taught you calculus. See? It was actually a lot easier than you think. Okay, just you find the area under the thing. It's calculus one, basically. I mean, there's a few other equations. But we're not going to actually do any like calculus in this class, so don't, it's the essence of calculus, which is you have a function, you find the area under a curve, which is basically height times width is a square. So find the area of a square. Okay. Anyways, here's a velocity graph. At t equals 4 seconds, the object has a position of what? Hmm. What is the position? Okay. Uh, we find the area under the curve. Okay, so let's break it down here. Now, I know I said calculus and you're probably still a little traumatized, but okay, what I'm saying is just find the area under this line and that tells you how far you traveled. Okay, so we're gonna draw this shape. I'm gonna make another plot here. Okay. Let me look at it. Okay, here's 4. Okay. We're gonna have 4, so this is, and then it's gonna go thusly. Okay, so this will be, what is this line here? Oh yeah, that's 2. Okay, so it's 2. 0, and then over here is 4. Okay. And then I've got 1, 2, 3, 4. Okay, so 1, 2, 3, 4. Okay. And I'm just gonna continue this line out like this. Okay. And so on the plot before, basically, you're cruising along here, and you have this velocity here over here. This velocity in meters per second. So you're moving at 4 meters per second. You're like, how many miles per hour is that? That is 8 miles per hour. Yeah, 8 miles per hour. You're going at 8 miles an hour, 4 meters per second. Like, oh man, I need some more beef jerky. All right, I'm gonna stop here. I'm gonna slow down. My velocity is changing, but how long did that take you? Or no, we want to know how far did we travel? Okay, under here. Okay, so I'm gonna make little squares. Okay, we basically just the answer. Remember this. Delta x. X equals v times delta t. Okay, well over here this is time, so we have time on this side. And we have velocity over here. Okay. So I see two shapes here. I see a box. I see a square. Can you see the square? Tell me you can see the square. I hope you can see the square. I can see it. Maybe it's like one of those things where you just have to look at it. You just have to look at it. Oh yeah, I can see it. One of those puzzles that like you have to stare at it in order for you to see that the hidden shape. Okay. Oh, I got a square here. My square is 2 times 4. That's 8. Okay. And I also have a triangle. Yeah, I got a triangle. Triangle. What's the formula for the area of a triangle? Okay, I'm gonna tell you the area of a triangle. Area of a triangle, hopefully you remember, but maybe don't. That's okay. It is base times height divided by 2. It's basically a square divided by 2. Okay, so my base over here, so the area of my square is of course 8. So here this is 8. Okay, so that basically is 8 meters over there. Then my base over here is also 2. I've got 2, and then my height over here is 4. Okay, so the area of my triangle is going to be 2 times 4. Put a little dot there for multiply. 2 times 4 divided by 2, which is 4, right? My 2's cancel. I get a 4 there. So my area of my triangle is 4. Okay, 4 meters. And over here on my square, I had 8 meters. So I'm going to do square plus triangle, okay, equals my distance, big D. Right. So D, my distance, is going to equal 8 meters plus 4 meters. So I traveled 12 meters. Okay. And you just found the area of these shapes. This is velocity versus time. Okay, that was easy. Okay, I can find the area of a square. I know how to do that at least. Yes. So my displacement then is 12 meters. Okay, that's probably enough for this video. Thanks for watching. That was section 2.2. Next will be 2.3, but we're gonna go a little faster. All right. Thanks for watching.